Hello, in this particular lecture we're going to have a look at AI decision-making techniques. By way of a bit of context here, this is building upon the AI agent lecture. So within that we saw that agents go through a number of phases. The first phase is where they sense about the world, things that they know. Thereafter they go into a thinking phase, is what we're looking at here, is where they decide based on what they've sensed, what actions should they take. And that is then followed by the actual execution of those actions. So in this particular lecture we want to have a look at a small number of common decision-making techniques. If we're thinking about this generically, and we do want to do it at this point because we're trying to present something here that really applies across most games, we can say that we have a decision-making process. As mentioned, it takes in information, things that you've sensed. Important distinction here is that we can do this two ways. If it's some external knowledge, so the location of the player or other characters, or whatever pickups you have in your world, that's external knowledge that can be fed into the decision-making process. Alongside that, we also have our internal knowledge. So we know about our position, our health, whatever states that we have. And that gives us our total information set that gets fed into the decision-making process. That process will give us an action. Now, we're not really interested in looking at the actions here because it does depend upon the particular game, but suffice to say that some of the actions may change an internal state, they may change the animation that we're using. Some of the actions may change an external, may change our position within the world overall, or to give a message to some other character. So what we want to look at then are three commonly used decision-making processes, and these three really do cover sort of the bulk of different techniques that are used in terms of decision making. We'll start off with the most straightforward one, which is the use of decision trees. Decision trees, they're very broadly used. They actually lend themselves well to embedding expert knowledge. But I suppose one of the deficiencies is in terms of their scalability. Let's have a look at decision trees. So by a decision tree, we mean a tree-like structure. Now in terms of the branching factor, it can be whatever you want. It could be binary in terms of each node having sort of a true or a false set of directions coming out, or you could have as many as you want depending upon the conditions that you're asking. For the nodes within the tree, the nodes up the tree, they contain questions or things that are evaluated. And depending upon how they are evaluated, or the answer to those questions, that determines which particular branch that you take from that particular node. As you go down through the tree making decisions, at some point you're going to reach one of the leaf nodes at the bottom of the tree. And each leaf node contains the action that you take. So you come in at the start, you evaluate the conditions, that leads you down through the tree. You get to a leaf node, that tells you your action. So hopefully you can see for this structure, it does lend itself to embedding expert knowledge. You can sort of ask your expert, well, what would you do? What would you think about? What decisions would you make? And to capture and encapsulate that information within our decision tree. Disadvantages are that as the reasoning process becomes more complex, it's more difficult to incorporate this within a tree-like structure. You don't have the notion here of sort of common paths or branching or going back or repeating things. So it's good for simple forms of decision making. Alongside decision trees, the other most common form of decision making is what's known as finite state machines. So a finite state machine, I mean, the name does give it away, it's a machine, it's an algorithm that contains or where you're in one of a finite number of states at any particular point in time. So it's saying then that a character, it can occupy one of a defined number of states. It might be sleeping, it could be running, it could be eating, it just depends upon the game which particular state it's in. When you're in a state, you're taking actions that are appropriate to that particular state. And the inputs to the system, they give you the reason why you would change from one state to another. So each state will have a range of transitional conditions that if this transition occur, or this condition happens, then I will transition to a different state. So if we think about it generically, we can say that each FSM has a number of possible states. You've got a number of transition functions that determine what states you can transition from and then go into. And sometimes you want to be restrictive here, that if you're in one state, you can only transition to a small number of the available states from this. And each transition, you would also give the conditions under which that transition would be triggered. Finally, when you're in a state or entering into a state, you would say what actions you take associated with that particular state. So this is presented generically here. FSM is very, very broadly applicable to really a whole range of different types of decision making. We'll give you a few examples now from a gaming perspective. So it works, FSMs work because they chop up the decision making process into a number of different smaller chunks. So in terms of states, in terms of actions, in terms of transitions. So it gives you an easier way of trying to model behaviour. And that's why they're so successful. Very widely used within games. You know, for example, we'll look at PACMAN, if you like, one of the sort of first FSM models. Beyond that, for controlling bots, for sports games or for real-time strategy games, FSMs really can be used in all of these. They're very much a sort of a staple of a lot of AI controlled techniques. So let's have a look at PACMAN as an example. So if we were to use the ghosts within PACMAN and to give them an FSM that defined their behaviour, we can say that there's three possible states that the ghost could be in. It could be in the wander state, where it's just wandering about the level. It could be in the chase state, where it is chasing the player's got sufficiently close and is given chase to the player. Or it could also be in the evade state, where the player has picked up the power pill and the ghosts are trying to run away from the player. And that sort of represents, if you like, the types of things that we want our AI agent to do. I mean, strictly speaking here, you could remove the wander state if you wanted to and just go for chase and evade, but keep wandering, it makes it more interesting. So having defined that, we can also say what transition conditions would make us change from one state to another. So if we're in the wander state and PACMAN becomes visible, PACMAN enters into whatever range we have, we could say that is our transitional condition to go from wander to chasing. And if PACMAN goes out of range, then we go from chasing back to wandering. Equally, when a power pill is eaten, then no matter if we're in the wander or the chase state, we automatically go into the evade state. And we stay in the evade state until the power pill has expired. And here we're making a decision. We're saying that when we leave the evade state, we don't have we're not saying sort of power pill expired and PACMAN isn't in range, go to wander, or power pill expired and PACMAN is in range, go to chase. Here we're just assuming power pill expired, go back to the wander condition. When we get into the wander, if PACMAN's in range, then very quickly we'll go to the chase condition as well. So having done this here, you can see it gives you a fairly easy, a fairly nice way of trying to encapsulate or define the behaviour of an AI-controlled entity. With for state machines, along with scripting as well, they are the most common forms of decision-making technique. Both of them they're relatively quick, relatively simple to debug, relatively simple to code. So they work in the majority of cases. Both of the approaches, they're relatively little computational overhead. Again, in both the cases, it depends upon the complexity of the transitional tests. It's either the decisions we're making in the decision tree or the transition tests that we're doing within our finite state machine. Both of them reasonably flexible. FSM machines, generally they're more easily extended, more easily modifiable. We'll look at a few, if you like, extensions to FSM in a second. And for the state-based behaviour of the FSM, it's particularly good for modelling a lot of entities within games. Generally, a lot of game characters do stick to one state and they do an activity associated with that state before changing to another one. It's maybe uncommon to have game entities that can have multiple simultaneous goals at exactly the same time. Let's have a look at an extension to FSM. It's an hierarchical FSM. And we'll start off with a problem first of all. So you see over on the right hand side a simple FSM. And it's for a robot that cleans up rubbish, trash. So initially it's in a searching mode. If it sees some rubbish, it heads for it, transitions into the head for trash, picks it up. Once it picks it up, it gets an item, it goes for the head for compactor, and then gets rid of that trash. Once the trash has been disposed, it goes back to search. So the basic behaviour here is searching for rubbish, picking it up, dropping it into the compactor, and repeating the process. If, however, we assume that the robot has a powered function, that this only has a certain amount of power, and whenever power gets low, it has to go and get recharged. So you can see there from the search, and from head from trash, and for head from compactor, we have another condition that if our power drops sufficiently low, we pause our activity, we go and we get power. When we're recharged, we then return to the activity that we were doing and carry on with that. So I mean, it makes sense, but it's a little bit cumbersome because we have the same type of activity from a number of different states. There's an easy way of getting around that, and that's through the use of what's known as an hierarchical FSM. It's where in the particular node of an FSM, we can actually have another FSM within that. So at the highest level, what we're saying here for the robot, it is either in the cleanup state or it is in the get power state. And any time that we need to get power, we'll go to the get power state. When we're finished, we'll go back to our cleanup state. In the cleanup state, we actually then have this internal FSM where we're searching or heading for trash or heading for the compactor. And this gives you a very elegant, very extensible and quite a capable way of representing more complex forms of behaviour. The final one we want to have a look at is known as goal-oriented behaviour. And this is actually useful in situations where you have a character that isn't single-minded, that maybe does want to have multiple things that it is trying to achieve. So decision trees, FSMs, don't lend themselves to this particularly well, but goal-oriented behaviour, GOB, does. So GOB is widely used in games such as The Sims. That would be a classic example of a game where characters have multiple goals that they're trying to satisfy. Now it could be emotional, it could be physical, motives, just depends on the game. It doesn't make any difference to this particular approach. It works for all of these. And other characteristic of goal-oriented algorithms is that you generally have a large number of actions that you could take. You're trying to work out what is the best action for me to take that will enable me to best satisfy my diverse range of goals. So let's look at an example. So we can assume that we have three goals, or three things that motivate us. And we're given here an insistence value. So a value of 0 means that I'm not bothered about it. A value of 5 means that I really am bothered about this. It's something that's important for me to do. So my three goals, I can either eat. At the minute I've got an insistence value of 4, so I'm feeling hungry. Sleep, insistence value of 1, so I'm reasonably awake. Or go to the bathroom, value of 3, so it's so-so. And I've got a range of actions I can do. I could eat some food, or eat a snack, or sleep in the bed, sleep on the sofa, drink cola, visit bathroom. And these are the actions I'm choosing between, and you can see that depending upon the action that I take, it will affect my insistence values. So eating food means that I get less hungry, but I increase my need to go to the bathroom. So the question is, based on those actions, what's the right one to pick that keeps me as content or as happy as possible given the different insistences that I currently have? How they do this, there's different ways, but one good way is the notion of discontentment, basically unhappiness. And one way we can measure this here is the sum of the squares of the insistence values, and then to work out from that which one we would pick. So for example, let's look at eating food. If we were to eat food, my insistence value would go, for food, would go from 4 minus 3 down to 1. My sleeping will remain the same, and my bathroom, need to go to the bathroom, will increase from 3 up until 4. So if I were to take that particular action, then my overall discontentment would be 4 minus 3 squared, which is just 1 squared, 1, plus sleep, 1 squared, plus 3 plus 1, the bathroom, 4 squared. That gives me a total discontentment of 18. If I then did that for each snack, you can see all the figures down at the bottom, my discontentment value would be 14. So if I were to eat a snack, I would be slightly less discontent, in other words, more happy. If I were to sleep in the bed, in that sense, I'm increasing, my discontentment goes up to 25. If I were to drink a cola, particularly bad thing, my discontentment goes up to, from 25 and then up to 35 for that one. So using this here gives you a fairly nice way of then choosing which action is appropriate. It works well because you can dynamically determine the list of actions depending on the objects that are in the environment. They can add more actions into it. More advanced approaches, they would take into things like, well, how much time does it take to actually eat food? How much time does it take to eat a snack? Or how close or convenient are these things? And again, that can tie into some of the traits of the character as well. So key takeaways from this here for vast majority of games. Decision trees, finite state machines, they give you your bread and butter approaches to managing decision making techniques. If you do have a character that has multiple goals that are trying to be satisfied and there's multiple actions you can take, then things like goal oriented behaviour, they give you a particularly effective way of managing that.